Today we are going to learn how to utilize the partial derivatives to locate extreme values in multivariable functions. So it's going to be about these extreme values for multivariable functions for f something like this with maybe two variables, x and y. And this can be extended to handle function with three variables, x, y, and z. This kind of application is widely used in many engineering fields, as it is related to the concept of optimization. I know that some of you might have heard about this word before, optimization, which, by the way, is about how to find the best or the optimal settings for any systems out there. So, what kind of extreme values are we talking about here? It turns out that we have two types of extreme values, and let's take a look at the first type on the left-hand side right here. Number one, the first type is going to be local minimum. Okay, local minimum. If you have just one of these, you are going to call it a minimum. But if you have multiple of them, like 2, 3, or 4, or maybe 10, you need to call them minima. So make a parenthesis right here that if it's plural, it's supposed to be minima, not minimum. Alright, now let's put a description to this local minimum. I like to keep it simple, so this one is going to be an easy to understand and easy to visualize version of that. So, local minimum is going to correspond to the lowest point. It's going to be the lowest point and lowest in terms of function value. So I'm going to put f right here to remind myself that it's about the function value that is being the lowest. Alright, now in the nearby area. And here comes the keyword, nearby area. When we talk about nearby area, we are talking about the close by surrounding, right? And the reason for that is because we are looking at the local minimum. Local, not global. So that's why we have this relation between this nearby area and this word local. And by the way, you can use another word to replace this nearby area, just in case you run into this word and you know that it has the same meaning. And this word is neighborhood. Neighborhood. Alright. Now that we have the description of this local minimum, let's take a look at an example of that on the graph on the left-hand side of the slide. So let's take a look at this graph right here. So on this graph, I have this function surface of some random function, and I'm going to call it function of x and y. Definitely a function with two variables, and that's why we have a surface in the space. So we want to find the local minimum on the surface by using the description, and from the description it's supposed to be the lowest point in terms of function value. So I look at the surface and it's quite obvious that the lowest point when it comes to the function value is at the bottom of this curve right here. So there you go. And when I look at the surrounding of this point, and this should correspond to the neighborhood of this point. Oh, by the way, I like to use this small ball to represent the nearby area or the neighborhood. And as you can see here in this area, there is no other point, no other coordinate that has the function value lower than this one. Alright, so this one is the lowest. So we can call it by confidence, with confidence that this is a local minimum. Local minimum. And that's because it's the lowest. Okay, now that we have the lowest point, there must be some highest point somewhere. And that leads to the next type of the extreme values, and that is number 2 right here. Number 2 is going to be local maximum. Once again, if you have only one of these, then you are going to call it a maximum. Let me fix this. This is supposed to be m. Okay, just one of these, you call it a maximum. But if you have multiple of them, like 2, 3, or maybe 10, then you need to call them maxima. So for plural, supposed to be maxima. Now let's put some description for this local maximum, and it's going to be similar to the one that we just did, except that this time it's going to be the highest point. Alright, highest point, and once again it's going to be in terms of function value. Okay, and same thing in the nearby area. And the reason for that is because we have this local again. So we have to talk about the nearby area. So let's find that in this example down here on the right hand side of the slide. And once again we have a function surface, and it looks different from the one that we had before. So I'm going to call it g this time, g of xy. And let's try to find the local maximum on this surface. And I'm going to use this description, highest point, in terms of function value. And from the shape of this, it's pretty obvious that the local maximum should be right here at the top of this. I'm going to call it a mountain or something. Okay, and if you draw the neighborhood of this point, or the nearby area, okay, you can see that there is no other point that has the function value higher than this one. So you can call with confidence that this one is definitely a local maximum. Alright, very easy, right? Local minimum, the lowest point. Local maximum, the highest point. Now that we talk about the local right here, the word local, I need to remind you something, which is that it's also possible to find the lowest and the highest points in the entire area or the space. So when we talk about local, we talk about nearby, right? It's possible to find ones for the entire area. And if you find them, we are going to call them absolute, minimum, and maximum. Okay, so make a note right here that it's also possible to find the one for the whole space. Absolute, minimum, and maximum. And this one is going to be for the entire area or space. And that is the main difference between absolute and local. Local is nearby, absolute is the entire space. But it's a little bit tricky to find those absolute min and max in multivariable functions, as it requires further proofs and other tests. So we will focus only on the local ones here. So don't worry, in this lecture and in this course, we are going to focus on just the local minimum and local maximum, not for the absolute ones. Okay, as you know, it's never convenient nor practical to find all these extreme values by graphing. As you can see here, we find this local minimum right here by looking at the graph. And same with this local maximum right here. We look at the graph and we can see the peak of this mountain. So in this lecture, we are going to learn some new techniques that we can use to locate these points by just calculations. No graphing, just working on numbers, and you can tell where they are. But the thing is, we are going to need to use calculus properties. So we have to bring what we learned so far in calculus to find these points. Well, the first thing we are going to do here is to do some observation. Alright, so let's do some observation at these local minimum and local maximum. The first thing that I see is that it seems like the surface is flat at these points. Whether it's at the bottom of this pit right here, it seems to be quite flat. Okay, and at the highest of this peak, it seems to be flat. So that is my first observation, and I'm going to write it down. So number one right here, the surface seems to be flat. And this comes from the observation. Right. Surface. Okay, let me fix that. I don't like it. A little bit crooked. So observation. So we see that the surface seems to be flat at these points. Surface seems to be flat. Okay. At these points, at these local minimum and local maximum, at local min and max, min and max. Next, we are going to translate this into some mathematic terms. Seems flat, it means that the slope at these points are supposed to be equal to 0. So let's translate this into slopes at local min and max are supposed to be equal to 0, and that's why we have the flat points. All right, it's right at the peak right here for the local max and right at the bottom for this local min. Now we have this keyword right here, slope equal to 0, and we are going to translate this further by using calculus. Talking about slope, okay, so now we add calculus here. Talking about slope, we are talking about the first order derivative, and now we are working with multivariable function, so it has to be first order partial derivative with respect to the first variable has to be equal to 0, right? Slope equal to 0. But once again, we have a variable y to work with too. So not just x, this has to happen too. df by dy has to be equal to 0. And there you go. We have got well, I could say that it's the mathematical properties at these local min and max in terms of derivative. Okay? Now that we have this property, let's take a look at what it looks like on the graph. So I'm going to erase this blue line right here and blue line right here. So talking about the partial diff of f with respect to x equal to 0. So we want to find the rate of change in the direction of positive x. Since this graph doesn't have the x and y axis, I like to add it to this graph. X right here, and x right here, and y right here, and y right here. So let's take a look at this df by dx, the first one equal to 0. It's going to be the change of the function value at this point, moving in the x direction, and it's going to be this, x direction. And right here, this is supposed to represents df by dx equal to 0. It's supposed to be flat. And for the df by dy right here, once again supposed to be flat, right? So we are supposed to find the rate of change in the y direction, and it's going to be in this direction right here. All right. So this line should represent df by dy. Okay, I need to move so that you can see. This is supposed to be df by dy equal to 0. Okay, so these two lines represent the properties that we just found. Same with the local minimum right here. df by dx is going to be the change of function value in the direction of f, x. So it's going to be in this direction. Okay, it seems to be flat. So it's going to be df by dx equal to 0. And then we have this df by dy equal to 0 too. It's going to be in this direction. And this one is not so clear, but you got the idea, right? df by dy is supposed to be equal to 0 here. So there you go. We have this one very important properties to be used. Now the question is this information that we found enough to guarantee 100% that these points are either min or max? So let's find out about that in the next slide. So in this slide, we want to check whether this condition of df by dx, first order partial diff of f with respect to x equal to 0, and df by dy equal to 0 is enough to guarantee local min or local max. So that is the question. So we want to check whether this can guarantee, all right, guarantee min or max. Question, by the way, not the statement. So we want to find out, and let's take a look at this example down here. It's a strange looking function surface. So let's call this function surface of this f of xy. All right, and we are going to study something at this particular point at the middle, at the red dot. Okay, so let's find out about this df by dx, the change of function value in the direction of x. Okay, so we are going to study the function value in this direction, positive x. So I am going to start right here, And as you can see, as I move along the function surface, the function value starts to increase. When function value increases, it means that the slope is positive. It means that df by dx is positive. So right here, I know that df by dx is greater than 0. And function value keeps increasing until it gets to this point, and then it starts to go down. Maybe something like this. Okay, when the curve goes down, it means that the function value goes down as well. And it means that the rate of change of f with respect to x has to be less than 0. So we are going to have this df by dx less than 0 for this portion of this curve. And as you can see here, we transition from positive right here, down here, positive to negative. That means that it's supposed to have some point that connects them, and it's supposed to be 0 in the middle. So right here in the middle, the transition between positive and negative. So right here we are going to get this df by dx equal to 0. And of course it has to be flat. So right in the middle, transition from positive to negative, and we have this df by dx equal to 0, and it's flat. And there you go, we have this first property for this point. Okay. Now, why don't we study the rate of change of function value in terms of y variable? So let's take a look at the y direction. So y moves in this direction. So we are going to study the function value in this direction. And I am going to start at this point right here at the top. And as I move further in this direction, the function value starts to decrease. Alright? When function value decreases, it means that the slope is negative, and it means that the rate of change has to be less than 1. So make a note right here, df by dy for this portion of this curve is going to be less than 0, negative. Alright, and it keeps decreasing until it gets to this red point in the middle, and then it starts to climb up. Alright, starts to climb up. It means that function value increases, and it means that df by dy is going to be greater than 0 for this portion. So for this case, df by dy is going to be greater than 0 or positive. So there you go, we have this transition from negative to positive. It means that there must be a point that connects them together right in the middle. So we have this right here, df by dy equal to 0, changing from negative to positive. What about I use this blue that makes you a little bit clearer to see. Right in the middle, here we have this df by dy. Okay, why don't I move it to right here, easier to see. df by dy equal to 0, and it's flat. Alright, so we have shown that at this point we have these two properties. First of all, df by dx equal to 0. First one right here. And then we also have this df by dy equal to 0, and that is the second one. The question is this point a local min or a local max? So let's take a look here. First of all, let's take a look at the x direction. What kind of shape do we have here? This curve goes up, alright, and then we reach the top of this point at this point, and then it goes down. From the look of this, it's definitely a local max, right? Go up and then go down. So you can make a note right here that this is a local maximum in x direction only. In x direction, right? Because we were following this line, and this is in x direction. What about in y direction? We already have local max in x. What about y? Let's follow this. Goes down, it goes down, and then reach the bottom, and then goes up. From the shape of this, definitely a local min. Go to the bottom of the pit. So local min in y direction. So we have a conflict right here. In one direction it's a local max, and in another direction it's a local min. Okay, local min in y direction. So let's make a conclusion right here that this is definitely not a local min nor a local max. Neither local min nor local max. Alright, so when you see this kind of shape, local min in some direction and local max in another direction, we call it a saddle point. Alright, why is it called a saddle point? Because it looks like a saddle seat you put on a horse, so that you can sit on the horse. Okay, so which means that this properties alone, this df by dx equal to 0 and df by dy cannot guarantee because we have this counter example. No, cannot guarantee. So in order to find this real local min and local max, we are supposed to do some extra calculations, and let's take a look at that in the next slide. Here we have a guideline on how to find the local min and the local max, and it's going to be for both the single variable function f of x and the multivariable function f of xy. Why don't we start with this one first, the version for the single variable functions, and we are going to find out about the steps that we need to take in order to find out about the local min and the local max. So first of all, as you can see here, the thing that we need to do first is to perform the first derivative test. So it's going to be about this f prime of x, and we want to find all the flat points, all the points that have the slope equal to 0. So we want this to happen. df by dx, the first order derivative of f with respect to x, to be equal to 0. We want to find all these points. And once we found them, we are going to call them critical points. Okay, critical points, they correspond to the flat points. And as you know, critical means important, but the thing is we don't know what kind of points they are. Critical points can be local minimum, it can be a local maximum, or they can be something else like inflection point. And that's why we need further test in order to determine its type. And that's why we need this second derivative test. And as the name suggests, we are going to need this second derivative, f double prime of x. And we do this in order to determine the type of the critical points. To determine type of critical points. Alright, so we have some conditions right here, and it's going to be based on the value of the second derivative. So let's take a look here. First one, if the second derivative f double prime of x is positive, then you get a local minimum. Alright, the way I memorize this is that I make it a little bit more interesting. When second derivative is positive, positive is good, and you have a smiley face. So you get something like this shape. With this shape, you are going to get this value, and it's supposed to be local minimum. Alright, it's just my way to make it fun. So next condition, second derivative less than 0, so it's going to be negative this time. Second derivative being negative, negative is bad, so you have a frowny face. Frowny face, you have this mountain right here, and you have this local maximum at the top, so that's why you get this local maximum for the second derivative being negative. And for the last condition, you have this f double prime of x equal to 0. If you have something like this, you have this inconclusive as the conclusion. Inconclusive means that you don't have any conclusion about it. You don't know anything about it. It can be anything. So let's add it right here. Inconclusive means no conclusion. Can't tell anything. No conclusion. Or in other words, can't tell anything. Alright, and that's it for the version for the first, single variable function f of x. So why don't we move to the version for the multivariable function? And it's going to be quite similar. So we are going to start by the first derivative test. Once again, we want to find the flat points, and we are going to find that from the partial derivative with respect to each variable. So we have this condition. Alright, so let's make a box around it. df by dx supposed to be equal to 0, and it has to happen at the same time. df by dx equal to 0 and df by dy equal to 0. We want to find all these points, and once again we call them critical points. Keep in mind that we have and right here, not or. So both of them have to happen at the same time. Alright, once again, critical points, you can't tell whether it's going to be local min or local max. So you are going to have to follow some further test, and let's take a look at this second derivative test for this version. It's going to be a little bit different. So second derivative test, which means that we are going to rely on the second order derivative, right? So before we first derivative, we rely on this fx and fy. For second derivative test, and let's take a look here. First of all, you are supposed to find this d value. So let me fix this box right here so we have more space. Okay. So this d value is very important. So first of all, find this d. Okay. This d value, and as you can see here, d value depends on some second derivatives of this function f. And first of all, we have this second order derivative of f with respect to x twice. Alright, and then it has to multiply with this second order derivative of f with respect to y twice. So we have this product for the front term. And then we have the subtraction of this, once again, second order derivative of f with respect to x and then y. And we are supposed to have this square right here. So first of all, you need to find this d value. And after that, we can use it to determine the type of the critical points. And once again, let's take a look at these conditions right here. We have 4 conditions. If your d value turns out to be positive, and that's why I told you we need this d value. You can make a note right here that we can call it d value. If your d value turns out to be positive, like this condition A, and the second order derivative of f with respect to x twice is positive, then you are going to get a local minimum. Okay? And you can call it a smiley face, right? Second order derivative greater than 0, positive. So we have this local minimum. Now let's take a look at this condition B. If d value is positive, alright, and then the second order partial derivative of f with respect to x twice is negative. Negative is bad, so we have this frowny face. So we are going to get this kind of shape, and it's going to correspond to the local maximum. Alright. So far d has to be positive. So d positive right here and d positive right here. What happens if d is negative? And that is condition C right here. When d is negative right here, if you get this, you know right away it's going to be a saddle point. And by now you know what this saddle point looks like, right? And let's take a look at the last condition. We have this d equal to d value equal to 0. If you get this, then it's inconclusive, which means that we cannot tell anything about it. So for this last one, d equal to 0, you can't tell. It means that no conclusions. No conclusions. So for the multivariable function of f of xy, you need to follow this guideline. And in the end, you are going to be able to tell whether you have local min, local max, or a saddle point, or you have something that is inconclusive. Now that we know about this guideline, let's try that on some examples here. So let's move to this example number 1. In this example, we have a multivariable function f of xy, and we are supposed to find all the critical points of this function, and after that we are supposed to determine their types. And of course, this means that we are going to need to perform both tests on this example. The first derivative test is going to be for the critical points, and then the second derivative test is going to be for the types. So let's get started now. First, we are going to perform the first derivative test. And in order to do that, we need the first partial diff of f with respect to x. First order partial diff of f with respect to x, and we can call that f with respect to x, like this. So we need to diff this function right here with respect to x only. So diff this with respect to x, I get, of course, the first term, I get this 4x. Diff this with respect to x, of course, I get 0 out of that. And then I need to diff this with respect to x, I get minus 2y. And then diff this with respect to x, I get minus 8. And then diff this with respect to x, I get 0. And the last constant with respect to x, of course, I get 0. And then I need to find this first order partial diff of f with respect to y. With respect to y this time. So this f with respect to y. And it's going to be equal to, I need to diff this same function with respect to y. This goes to 0. This becomes 2y. Alright, and then I diff this with respect to y, I get minus 2x. And next term, this one with respect to y goes to 0. And this one with respect to y, I get minus 2. So there you go, I have this fx and fy. And as you know, the first derivative test require both fx and fy to be equal to 0. Because they want the flat points. They want the slope to be equal to 0. Slope right here, df by dx equal to 0. And slope right here in the direction of y to be equal to 0. And right now we have two equations to work with, so let's bring it down here. I am going to bring the first one for the fx down here. It's going to be 4x minus 2y, and then I move this 8 to the other side. Alright, so I have this equal to 8. And then I bring the next equation of 2y, and this comes from the fy, minus 2x, and then I move this 2 to the other side. I have this equal to 2. And then I can combine these two equations together, plus them, add them together, and then I can get this. Okay, 4x minus 2x, I get this 2x equal to the 10 on the other side, which means that I get this x equal to 5. Alright, by solving these two equations, I get x equal to 5, and then I plug this x equal to 5 into the equation, and then I get this y value out of that. Okay, y to be equal to 6. Okay, so there you go, we got this critical point, just one of them, for this example. So you can make a note right here that we found one critical point from the first derivative test. Critical point, and it happens at the coordinate x equal to 5 and y equal to 6. Okay, so we are done with the first task, finding all the critical points, just one this time. Now we are supposed to determine their types. We are supposed to determine the type of this 5, 6. So as you know, we are going to need the d value. So let's take a look at the formula for d value. We are supposed to find this d at this point, 5 and 6. Okay, and as you know, we need the second derivative of f with respect to x. This comes from the formula. At this point, oh by the way, x twice, at this point 5 and 6. Times partial diff of f, second order with respect to y twice, at same point 5 and 6, minus partial diff of f, second order with respect to x and then y at the same point, 5 of 6, and we need to square this one. Alright, so we need to find these values in order to find the d values. Okay, so we need to find this one, and this one. So we are going to work further from this. Fx equal to this 4x minus 2y minus 8, this expression of first order partial diff, and this one too. We are going to diff this first one with respect to x, alright, with respect to x, and we are going to get this f with respect to x first and then x later, and it's going to be equal to, let's diff this with respect to x. This one I get 4, and this one I get 0, and this one I get 0. So second order partial diff of f with respect to x twice is a constant 4. Now I need this f with respect to y twice, so I need to diff this again with respect to y. And I am going to get this f with respect to y and then y again. And it's going to be equal to, now let's diff this with respect to y. I diff this with respect to y equal to 2. And diff this with respect to y equal to 0. Constant here goes to 0. And once again, this second order partial diff is a constant and equal to 2. Now we need the last term, f with respect to x first and then y. So I need to work on this one. I need to diff this with respect to y. And in this case, I am going to get this f with respect to x first and then y later. And it's going to be equal to, I need to diff this with respect to y. This goes to 0. This one with respect to y, I get minus 2. Alright, this one is minus 2. And last one with respect to y goes to 0. So all of them are constants. So let's use them in the formula down here. So this is going to be equal to f with respect to x twice, and that is equal to 4, times f with respect to y twice, and that's equal to 2, minus f with respect to x and then y, that is minus 2, and we have to square them. So in the end, we have this 8 minus 4, and that's equal to 4. Alright, and that is the d value. And one thing we know is that this 4 right here, d of 5, 6, at this point is positive, greater than 0, because we have this 4 right here, positive. Now we can use the guideline that we learned about earlier, and we have all these conditions. So let's take a look here. D at this point, at this critical point, 5, 6, is positive. Okay, because it's equal to 4. And then the f with respect to x twice, the second order partial diff of f with respect to x and x is equal to what? Equal to 4, right here. So it's also positive. So we have this condition, both of them. And as you can see, we have this d as positive and then f positive. So we are going to get this smiley face. Smiley face, and we have this kind of shape. Of course, is going to be a local minimum. Okay, so from this you can conclude right away, a local minimum. Okay, let me move this smiley face. Local minimum. Alright, at this critical point of 5 and 6. Well, by now you can call this 5, 6 a local minimum. So once again, we have this smiley face, positive, and we have this local minimum. Okay, not bad, right? Now let's try one more example. This example number 2. Once again, we have a multivariable function f with two variables x and y, and it's equal to these terms. And once again, we are supposed to find all the critical points and then determine their types. So we need to repeat everything again. So let's do that first with the first derivative test. Number 1, first derivative test. And we need to find the partial diff of f with respect to x first. And then it's going to be equal to, let's diff this with respect to x. This one with respect to x, we get 3x squared. Alright, diff this one with respect to x, we get 0. This one with respect to x, we get minus 3y. So there you go, we have this minus 3y. And f with respect to y equal to, diff this same function with respect to y, First term goes to 0. Second term becomes 3y squared. So 3y squared is what we get for this one. And then diff this with respect to y, we get this minus 3x. And as you know, the first derivative test requires both fx and fy to be equal to 0. Once again, this have to be equal to 0, and same for this one. Slope has to be equal to 0. Slope has to be equal to 0. So we are going to work on these two equations again. So first equation from fx, 3x squared minus 3y equal to 0. Second equation, we have this 3y squared minus 3x equal to 0. And I am going to divide both equations all the way through with 3. And this 3 is going to go away, same with this, same with this, same with this. So let's take a look at what happened to them. So here we are going to get this x squared equal to y. Alright, and then for the second equation, we have this y squared equal to x. So the next thing I'm going to do is to put this equation into this x right here, because x equal to y squared, right? So the first equation becomes this y squared. Square again. Okay, y squared square again and equal to y. Alright, what about I do something differently? I like x variable better. Well, this one is not wrong, but I like x better. So let me change on this one. So instead of that, I am going to work on this one, y equal to x squared, right? So I am going to put this into this y right here. And I am going to get this x squared inside and then square outside. And it's going to be equal to x, and this is based on the second equation. So in the end, I am going to get this x to the fourth equal to x, right? And then I can move x to the other side. I get this x to the fourth minus x equal to 0. And then work on this one on some factors. I get this x in the front, common terms, x cubed minus 1 equal to 0. And you solve this equation for the x that make it true. And as you can see here, two values of x that can make this equation true. X equal to 0 and x equal to 1. And when x equal to 0, then y is going to be equal to 0 as well. Y is going to be equal to 0. Look at this. X equal to 0, y of course has to be 0. If x equal to 1, then y equal to 1. This means that we have found two critical points. Alright, make a note right here. Found two critical points. Points, two of them. One at 0, 0. Okay, I'm supposed to put at right here. At 0, 0. And the next one is 1 and 1. Okay, these 2 points. Okay, 1 and 1. Now, I am supposed to determine their types. And of course, I need to check their d values. So first of all, I am going to find the second order derivative of this function. So first of all, let's take a look at this fx again. Okay, we are going to need to do this dxy, this d value. So we need this fxx times fyy, alright, minus fxy squared. Since we have 2 points to check, I am going to work on this equation first. Alright, so we have this equation right here. So first of all, I am going to find this f with respect to x twice. So I am going to diff this with respect to x. So diff this with respect to x, I am going to get 6x out of that. So this is going to be equal to fxx equal to 6x. And I diff this with respect to y. So I am going to get this f with respect to y twice, and it's going to be equal to 6y. Alright, so it's going to be this one. Now I need the last one. Oh, by the way, square is not supposed to be here, it's supposed to be at the top right here. Now, fxy, I need to div this. First one with respect to y again. Okay, and I get this minus 3. F, x, and y equal to a constant of minus 3. So we are going to use all of them in the formula down here. And it's going to be equal to this fxx. This is going to be equal to 6x, and fyy, 6y, and minus fxy, that is minus 3 squared. So in the end, we have this 36xy, xy minus 9. Now let's check the d value at these 2 points, at 0, 0, and 1, 1. First one, let's change color to blue. D value at 0, 0. Let's check on that. Equal to 0 gonna go in here, 0 goes in here, so we get this minus 9. And as you know from the guideline, if the d value is negative, right here we have this d negative, and it's going to mean that this is a saddle point right away. Okay, so 0, 0 right here, saddle. Now let's check the 1, 1. What's going to happen? D 1, 1. It's going to be equal to 1 goes in here, 36. Alright, times 1 and 1. Minus 9. And it's equal to 27. Okay, so what we have right here is D positive. That's good. So it means that we are supposed to check the second order partial diff at xx at this point. So we are supposed to check on this one, fxx at 1, 1. So it's going to be equal to, put 1 in here, we get 6 out of that. So here we have this fxx equal to 6, right? It's going to be positive. Positive, once again, it's a smiley face. Okay, we have the smiley face from this positive. So smiley face, once again, we are going to get a local minimum at this point. So smiley face, so you can make a conclusion right here that this is a local minimum. And you can make a conclusion right here. At 1, 1, this is local min. And that is the answer for this example number 2.